Hi, so today what we're going to be looking at is the layout process of this RGB LED module controlled over CAN bus. This is a pretty simple design, but basically what we have is first a buck converter that takes the system 24 volts and converts it down to 12 volts, which will power the LEDs. We have low side drivers for each color channel of the LEDs. And we have a microcontroller which handles all the um, CAN bus communication and PWM for the LEDs. And we have the CAN transceiver. And we have a little linear regulator that supplies the 3.3 volts for the microcontroller. So I'm just going to do a time lapse of my layout process, starting from scratch and going to a completed PCB. And I'll be narrating over top of that. So let's jump right in. So you can see here, I've already got the board size defined, and I've got the mounting holes laid out. So those were my first orders of business. And then the next thing I do is start playing with connector positions, because those are going to drive the position of other components. Now I'm looking at the most critical or the most sort of demanding layout section, which is the buck converter. And I'm just playing with the layout of some components. I'm trying to get this input capacitor C4 to be really close to the power input to the chip. I'm also laying down some ground vias to get a good low impedance connection to ground. So I put a ground via down at every ground pad that is on the board. So as I'm going, I'm also fixing up the silkscreen designators. Oh, and here I thought that I might want the connector flipped around. So I did that. And now I'm thinking that the connector and buck converter should be down there. And now I'm fixing mounting hole positions to make them more precise. I think at some point I'm also editing the board shape a little bit so that everything is precisely where I want it to be. Yeah, the mounting holes are something you don't want to leave till last, because then you'll be struggling to stuff them in somewhere. Okay, so now I'm realizing that my connector should actually be flipped to the original orientation. So I go ahead and do that, and now it's back. And while I'm at it here, I go ahead and put in the silk screen. I make sure there's room for the silk screen text that I want. Because if there's not space for it, then I'll be sad later. So what's next? So next I'm placing the output capacitors of the buck converter. And pretty soon here I'm about to realize that the 2.2 microfarad capacitor is too low of a voltage rating, because it's like this little 0603 package, and the voltage rating is only like 10 volts or something. So I change it to a larger package so that can support some higher voltage rating. And so that requires me to change the orientation of that guy, but that's okay, because I'm going to put down vias to ground on the ground pad of that capacitor. Now I'm thinking about what I'm going to do with that bootstrapping capacitor. Although its position is not as critical as some of the other things. And yes, you can see that I jump around a lot between what I'm doing, but So I'm realizing that it's not going to fit there. And so then I think, well, I'll put it at the output of the switching node, and then I'll put okay, so now I'm, well, making sure I'm in the right layer. I'm drawing the copper that connects the connector to the input of the chip. We're making sure that's nice and wide and that it only necks down where it gets close to the chip. So now I'm setting up the traces for the bootstrapping capacitor. Now this is the switching node of our buck converter. So I'm making sure it's nice and beefy because it will be carrying high switch currents. Although it is a very small node, those switch currents can be high. And so we want to be sure that that is a low loss. And so now I've positioned my bootstrapping capacitor, and I go ahead and route that, fixing up some stuff. And now I'm going to do the solid region for the 12-volt output, just getting it started there. And then, so first I start by roughing in the shape, and then I use the modify polygon border to change the exact shape. So now I've gone and flipped that connector around because I figured it would make more sense to have the 12-volt supply close to the 12-volt output. So I've flipped that. Now again, I'm adding silk screen text because I know we'll need it later, and if I don't leave room for it, then I'll be sad. And then I do some noodling around here that I ended up undoing because I couldn't get it to look right. Yeah, just noodling around with silk screen sizes. And now I'm thinking, this is a little bit of a controversial move, making them at slanted at an angle like that, but it's all right. So now I'm doing the low side driving switches for the LED color channels, making sure to position silk screen designators as I go, just to make sure they fit. Laying down some vias because these are, a potentially high-ish current going through these FETs and through those vias. So I would make sure to lay down a few. Probably more than strictly necessary, but it doesn't hurt to have a little extra. So now I'm positioning the driver BJTs, or the sort of the level shifting BJTs and their associated resistors. And again, positioning silkscreen text so that it's readable and near the component that it's calling out. Laying down ground vias again. A ground via for every pad is a good practice. I'm searching for the next component. So now I'm going to do some more work on the support components for the buck converter. These are the feedback resistors here. Just arranging those. And these are the compensation components. Placing those in some kind of reasonable setup and fixing silk screen designators as I go. These are more support components that set the frequency and the soft start time. And the buck converter at this point is pretty much done. As long as your initial component placement, you want to spend a little bit of time on initial component placement for a switching converter, and then it sort of just falls together. Now I'm positioning the linear regulator. It's got a bypass cap really close to its input. Of course, ground vias. So now I'm drawing a copper region to provide a little bit of thermal mass to heat sink this regulator. I don't expect it to get all that hot. It should be dissipating less than a watt. But even at 1 watt, if it were dissipating that much, that's enough to warrant a little bit of heat sinking. And I'm positioning the output bulk capacitance for the 3.3 volt rail there. And I'm positioning these thermal vias. Well, what they do more than there are thermal vias, but also there are electrical connections between this the regulator and the internal 3.3 volt plane, because I'm imagining this board as a 4-layer board. Now I'm thinking about just taking the 12 volts and routing it down like so. And it may be controversial to route the feedback, in the same track as the power to the linear regulator. But the linear regulator is so low current that I'm really not worried about it affecting any accuracy. So now we're looking at I'm looking at the CAN bus section, mostly because it involves another connector that I've got to place. So that's what I'm doing here. Place the connector, and now I'm placing the termination resistor connection and all of these other support components. And then I'm realizing that I need to flip around the connector itself. Or have I realized that yet? Oh yeah, I did it real fast. Okay. So positioning, this is the bypass capacitor for this chip. And with bypass capacitors, you want to place them as close to the power inputs on the chip as possible. Whatever component it is that they're bypassing, you want it as close as possible so that you minimize the parasitic inductance in the traces. And right about there is where my recording software decided to stop working. So I lost a bit of work that I did, but I think it's fine that if we can just, we'll cover it now and I'll just talk about what I did. So first I want to shelve my polygons so I can see what's going on. Up in this section, this is probably the only other semi-critical thing, which is making sure that the connections from the connector here driving the LEDs can carry a fair bit of current. So we don't really know how big this LED string is, but our buck converter can put out about 5 amps. So, you could imagine, almost 2 amps per channel is possible. I also added something that wasn't there during that time lapse, but was there in the schematic I showed, which is a dip switch here, which is necessary for configuring the CAN ID. But let's look at some other things. I positioned the crystal oscillator. Well, it's a crystal. The oscillator is formed when you connect it to the microcontroller. It's only 8 megahertz, so it's not critical that there's like length matching or impedance matching. I just tried to keep it as short as possible and keep it as symmetrical as I could. On the bypassing of the microcontroller, I tried to use these copper regions to connect the bypass cap, to connect the via that goes down to the internal plane to the bypass cap and then to the power pin, and tried to do that to bypass the power pins on this guy. there's not much else to say. You know, I was was a little bit sloppy on the traces, on the routing, and it just ended up the way it ended up. But it's really not terrible. Um, I didn't. You saw everything that I did to the buck converter, so that's fine. Let's look at our planes now, or our polygon pores. So I'm going to restore those and repore. So starting on the top layer, we have just a polygon pore that is ground that connects all the ground pads up with the vias. You know, that's its main job, is to just connect all the ground pads to the bypassing vias, or sorry, to the ground vias. The second layer down, or internal layer 1, is a solid ground layer, you know, only broken up by the vias that had to be thrown down. And so that's what's providing a really low impedance connection to ground at all times. The internal layer 2, I've split it into two different planes. One plane is our 3.3 volt section, and the other section over here is our 12 volt section. It just made sense and it worked out that way. You know, everything was laid out in such a way that, you know, all the 12 volt components that needed 12 volts, I grouped together, and everything that needed 3.3 volts, well, that was everything else. So it ended up very neat that way. And the bottom layer is much like the top layer, where it's just tying up all the grounds. You know, we don't have a ton of traces on the ground layer, so the ground, like the bottom layer, almost could be good enough as is, but it's still really good to have this contiguous ground plane to give the current the best chance of finding its way home with a low impedance. I think that's about it. This board, you know, aside from I did some more silk screening. I try to be as descriptive with my silk screen as possible, so that as much stuff that I think I might need to know is printed on the silk screen. But aside from that, this design is pretty much done. The last thing I would do is add the names of the designers who worked on it, and probably the Crubotics logo. And then it'd be ready to generate the Gerbers and send to the fabricator. Now I just want to cover how to export the Gerber files, which are the fabrication data that we'll send to the manufacturers. So to do that, we're open with our PCB file. We're going to go over to File, Fabrication Outputs, Gerber files. Now you can do it Gerber X2 files, but Gerber files are sort of the old school standard. You can do inches or millimeters. It doesn't matter. It's called out in the header of the Gerbers. So we're just going to go with millimeters, and we're going to go with the highest resolution that we can achieve. You know, it shouldn't be a problem for any manufacturers nowadays. For our layers, I like to do used layers on, plot layers used on. And now I don't think we need mechanical 13 or mechanical 15. Most critically, it's that our mechanical 1 is our board outline. So that's important to export that. We should select use software arcs. That's usually a thing that you can do. And everything else is fine. Everything else is fine. And we just go OK. Now, the next thing that will pop up is this Camtastic file. But what it's doing is it's just displaying the Gerbers for you. So it's a file that just, it almost seems useless to me, but it's there, and it means that the Gerbers got exported successfully. And so here we are with all the Gerbers. And we can go ahead and save this Camtastic file. Something reasonable. And at this point, I usually like to use another tool to actually check the Gerbers and make sure they're right, or not something strange going on. But before we do that, we need to also export the Excel on drill files, also called NC drill files. So we're going to do that now. We're going to go to, this time again, fabrication outputs and NC drill files. Now again, we can do millimeters. 4 is fine. Reference to relative origin. We're going to click suppress leading zeros. We're going to generate separate drill files for plated and non-plated. That's all we need there. Now, before continuing, let's import drill data. We need to click units and make sure this matches, because if it happens to match, because it's leading zero suppression and metric, okay, looks good. And again, it's giving you a Camtastic file, which just shows you those drill drawings. Aside from that, I don't have much use for these, but it does show you that they exist. So let's save this again. Something reasonable. Save this again.